what happens if the universe is expanding? If you go back in time, what do these equations say? And these equations say that there comes a point in time, there's a time at which the universe, which was expanding, sort of contracts. Its density becomes more and more and more because it is same amount of matter is now compressed in a smaller volume, a smaller volume, and smaller volume, and therefore ultimately there's a point, or there's a time at which the matter density becomes infinite, and then by Einstein's equations, space-time curvature also becomes infinite, and if you like, the universe and the equation just stop. I mean, general relativity certainly allows a white hole. There are solutions in general relativity with white holes. All the physical quantities become infinite. When all the physical quantities become infinite, then it's called singularity. Then anything can come out of it, because infinity has an infinite reservoir of energy, the time, quantum, everything. So anything can come out of it.
So there are, sir, a lot of like documentaries and articles, popular science articles are there on the general relativity and also on gravitational waves. So these are kind of hot topics for the for what to say ki, whatever documentaries are there, they are hot topics. Like people like Brian Cox, Brian Greene, people like them are making very beautiful documentaries on these topics. So, what do you think? How do these documentaries? Does these documentaries really help a student or a person who is interested in kind of fields? And does they have any impact on the viewers?
Yeah, so I think that for beginning researchers, good documentaries. That's a problem. That there's a lot of things which are just plain wrong. I mean, there are documentaries that are just plain wrong. So that's the problem. That there's too much information. I mean, it's a delightful thing that we're in the information age and we've got so much information so easily accessible. It's very, very good. But there's also, because there is so much, because anybody can put information out there, you have to be very discriminating. You have to be very careful about what you read. So the good documentaries can be very helpful to young researchers and young students, and of course they can help public at large. Now there are two different things here. One is, it is really important to disseminate this knowledge to public at large also. People who are not going to be scientists, but hopefully they are curious enough to know how the universe works. And for them, it is very important because after all, they are the taxpayers. They are the ones who are going to be driving how much researchers go and resources go into scientific research and so on and so forth. So it's important. So that is one goal. And the second goal is younger generation who can learn about more in more detail, more accurately. And particularly for the second goal, the younger generation, beginning students and researchers, for them, good documentaries can be very helpful. But in some sense, they should always have a little grain of salt. Don't accept everything that is in the documentary, because there is a lot of also an agenda behind particular people. Some people might push their favorite ideas, for example, string theory, way beyond it is really justified. That way, so you have to take things with a grain of salt, and trust things that are observationally actually uh, uh, verified, and not. I mean, there are all kinds of ideas about, for example, how there will be drastic effects even well outside the black holes where general relativity would fail. This was called firewalls in the string theory scenario. There was called, then after that, it was people thought that ordinary quantum mechanics, ordinary quantum field theory would fail out of the black holes. None of this turned out to be true from the, from observations. And LIGO observations work perfectly fine with classical general relativity. So I don't mean that people should not work on these ideas. I think science is driven by competition of ideas, and one should have unconventional ideas. That is perfectly fine. But it is communicated to the public or to beginning researchers, particularly. I think that is there's a whole bunch of researchers going to areas thinking that this is the ultimate truth. And in fact, there is very little justification for that. And that has to be avoided. So I mean, all these ideas um, about these firewalls and failure of general relativity outside black holes and so on. We again got a lot of publicity, but then now that after LIGO discoveries, it just quieted down. But there's no documentary, no publicity. We said, well, look, those ideas are wrong. So students don't know that. They think that those ideas are still valid. And that, I think, is a little bit of a caution that is needed there about.
Ji. So, one more thing that I would like to ask about what comes as a result of these articles and the documentaries, that a question arises about the counterpart of a black hole. Like it eats all the things. So, is there a counterpart which just releases energy without taking any? Is there a white hole?
Yeah. So the
topic like singularity, let me ask something about the origin of universe that has also been a part of your research. So the early stages of universe, and please tell us something about. There is a popular theory called Big Bang, and it is very popular to explain the origin of universe. And then there are certain questions arises that where does that thing came from, which started the universe? Where does that bang happen? From what it happened? Where does that singularity came from? So there are a lot of questions. So if you can just अगर आप उन चीज़ों को एड्रेस करेंगे, so that will be a really helpful for students, so to understand what exactly is going on in scientific research.
Very good. So, right. So, I mean, if you go back to Newton, for example, what Newton did was to really do something totally spectacular. Namely, he said that there is a universal law. And this exactly the same equations that govern apple falling on Earth govern moon going around Earth. It's exactly the same equation. So you say, well, you're out of your mind. I mean, apple falling is one trajectory, moon going around look completely different trajectory. How can it be that is the same equation? But only the initial conditions are different. The initial position and velocity of the apple and the initial position and velocity of the moon at any instant of time and that of the apple at any instant of time are different. But with exactly the same equation gives me the trajectory of the apple and the trajectory of the moon going around Earth. If I put in the velocity and the position at any instant of time, and this is spectacular. This shows universality, right? And that is what was so profound about Newton's law. Well, Einstein elevated it to a completely higher level. Namely, he wrote down these equations, and these equations again, they explain the motion of the moon around Earth, but they also explain formation of black holes, and they also explain how the universe by itself, they can be applied to the universe as a whole, not just to the moon and solar system, but to the universe as a whole. So as a universe as a whole, what is this dynamics? And there's a long history, and I don't want to go into it, but in the early days, there was a lot of controversy about using Einstein's equation to say what happens to the universe as a whole. And I want to say that this is a new paradigm. This happened only after general relativity, that we can try to apply, that there are some equations available that can be applied to the universe as a whole. And I mean, of course, only to the large scale properties of the universe. Einstein's equations will not tell what happens in small fractions of the universe, but they will tell you very well what happens on a large scale structure of the universe. On large scales, how is the universe behaving is predicted extremely well by Einstein's equations. So the statement is that so and then the statement was that, well, okay, so now we know that the universe today is homogeneous and isotropic. In other words, if I look at one instant of time, I look at anywhere around me, I see on a sufficiently large scale, I see the same distribution of matter and so on. Of course, in the solar system, that's not true. I mean, there is matter in the sun, and there is no matter at the edges of solar system. But if you average out on large distance scales up here, then the universe looks very homogeneous, and also there does not seem to be any preferred direction. So this is, if you like, the Copernican principle, but applied to the universe as a whole, much more grander than the solar system. There's no preferred place, and there's no preferred universe. Now, if you apply these to Einstein's equation, then you are led. Einstein's equation tell you, and this was something that was discovered by Friedman some time ago, and the Russian cosmologist, and then independently discovered by Lemaitre, who was a Belgian astronomer, cosmologist, physicist. And so this, and then one can just ask what happens if the universe is expanding. If you go back in time, what do these equations say? And these equations say that there comes a point in time, there's a time at which the universe, which is expanding, sort of contracts, its density becomes more and more and more because it is same amount of matter is now compressed in a smaller volume and smaller volume and smaller volume, and therefore ultimately there's a point there's a time at which the matter density becomes infinite, and then by Einstein's equations, space-time curvature also becomes infinite, and if you like, the universe and the equation just stop. They lose all their predictive power. And so this event is called the Big Bang. And the idea was that the universe began with this Big Bang singularity. We say singularity because everything is becoming infinite, as I mentioned before. Then all the physical observables become infinite. That's called singularity. So here the matter density and the space-time curvature, they all become infinite. And so that is called that prediction of general relativity is that the universe began with a Big Bang. Now, this was not accepted universally. People didn't like the idea of a finite beginning and so on and so forth. So people like Fred Hoyle particularly and Jane Narlikar in India, and they had proposed another model of the universe, which is called steady state universe. But as time went on, it sort of became clear that model is not viable, and the universe did begin early on. The universe is evolving. It's not in a steady state. That's what became clear. So if you use general relativity, then you get the conclusion that the universe began with this Big Bang. However, I should say that Einstein himself, this is an important point, and also Lemaitre, they were not so sure that this mathematical prediction really reflects physics. And Einstein has a very beautiful quote which says that we should not take the field equations, he means his own equations, and assume their validity all the way to the Big Bang. Okay? Since that some stage completely. But nonetheless, it was ignored. And so the notion of Big Bang has really taken over. I mean, it's become a standard notion up here for many, many decades, right? But the statement is that what Big Bang or singularities mean is that the theory has lost its predictive power, right? Because equations fail, quantities become infinite, and then you cannot evolve, you cannot time evolve, you cannot predict what happened before the Big Bang, for example. The equation just failed. John Wheeler used to say that if you put these equations on a computer, then there will be just smoke, and the computer will burn up, and there'll be a smoke, and there'll be no prediction. So what is the status currently? So there's a very nice video. I can send you the link of this, which is in which 7 of us were interviewed, and we were interviewed separately. It's completely different locations. There was Roger Penrose, there's Stephen Hawking, there was Alan Guth, there was Alex Vilenkin, and I was interviewed, and other people, a couple of other people were interviewed there, and we were asked about the beginning of the universe, is this point up here, and we have been following various quite different approaches, and we were interviewed in different cities, and we did not know who else was being interviewed. Yeah, there's also Veneziano, who was one of the founders of string theory. But we all uniformly said the following, that Big Bang is a prediction of a general relativity, which is just an indication that the theory fails there and we need a better theory. So that always happens in physics. When theory predicts something infinite, then that means that the theory is, we're pushed it beyond its domain of validity and we need a better theory. And this better theory in some ways is something like quantum gravity. All of them say that some idea about unification of general relativity and quantum mechanics is needed. Of course, all 7 people have different ideas about how we should be really, what is the correct approach. I mean, we're following our own approaches because we think they are most promising. But the nice thing about science is that finally nature decides. But I think variety of approaches is very, very important to make progress. I mean, everybody should not follow the same approach, and that would be a big mistake, especially when the experimental data is not so. So all of us came to this conclusion that there was definitely a very hot phase, early hot phase in the universe. But this is not where everything blew up and everything became infinite or anything like that. Universe has been cooling down since then. Now, what happened before that hot phase? None of us believed that there was a singularity. In other words, there was a Big Bang in the traditional sense of the word. You can say that this hot phase of Big Bang in some loose sense of the word, but it's not really the Big Bang in the traditional sense of the word at all. And that none of us thought that there was actually a singularity. So I think it is quite reasonable to say that there's a consensus on this matter. Now, this brings us to a very interesting point, and which is really relates to what you're asking me just a few minutes ago about usefulness of these videos or popular articles and so on and so forth. So, for example, loop quantum gravity that I worked on has a prediction which says that, in fact, so Big Bang, there was no Big Bang. So what happened? So we have a prediction that, in fact, if you combine general relativity with quantum mechanics, then Einstein's equations get modified, they get corrections. And then if you use the corrected equations, interestingly, the corrections are almost negligible until you come very, very close to the Big Bang. And this is a prediction, it's not put by hand. I mean, it was surprising, it came out that way. And then very near the Big Bang, however, the equations predict a different trajectory, different solution than what is predicted by general relativity. And matter density becomes extremely large, but not infinite. And at that time, effects of quantum gravity, or what we like to say, is the effects of the quantum mechanical nature of the very geometry of space and time. Einstein taught us that geometry of space and time is a physical entity. So in loop quantum gravity, this geometry is not a smooth continuum. It also has microscopic structure. Just like the screen you're seeing in front of you looks continuum, but if you put under an electron microscope, it has atomic structure. So the very space-time geometry has an atomic structure. And in general relativity, you can ignore the atomic structure until you are near the Big Bang or near the singularity of the black hole. But then the true equations are quite different from Einstein's equation, and the Big Bang is replaced by a big bounce. That's what we're saying. So I don't know when it was, probably around about 20 years ago, a little less than 20, but about 20 years ago, Scientific American had a big cover article saying that there's no Big Bang. Big Bang is replaced by big bounce. And I think it was a bit premature because these are the very promising ideas, but these observational things are not. But just recently, like last month, they had not a cover art feature, unfortunately, and I don't know if it is in the printed version, but an online article with a big headline: "The universe began with a big bang and not a big bounce." So opposite. And these are sensational articles. And if you look at, I was very disappointed with Scientific American because there are many articles that are good, and I encourage my undergraduate students to read some of those articles, etc. So I did write to the editor of the Scientific American and said that, well, what you're saying is incorrect. And these recent investigations, which are very, very good, show is this, but they don't say that there was no big bounce and that was the Big Bang. And as I said before, all 7 of us, like Stephen Hawking, Roger Penrose, Guth, Belinkin, Veneziano, and we all are saying the same thing, that there is no big bang. And then for Scientific American to come out and say something like that is a little bit irresponsible. So I think that this is an example. Just it came out because of your question. This is an example where I would say that that's why I'm very weary about young students just reading something or seeing some news article and thinking that this has been established, and it has not been established. So that's where this discrimination I was talking about really astutely choosing your sources is really important.
जी, जी, जी. So, LIGO India, there is a project that is going on in to understand the gravitational waves. LIGO's was another project, and it's the Indian star. So you were a part of the committee to, and you were the you were one of them there who talked to the authorities that this should come to India. So please tell us something about why you wanted that to come to India, and what are the things that it can explore to understand more about the universe and the gravitational waves.
Okay, so let me just sort of slightly correct what you said. I mean, it's not what you say is not wrong, but it's a little to simplify. So what happened is that currently this LIGO observatory, LIGO stands for Laser Interferometric Gravitational Wave Observatory, and this is currently there are two detectors in the United States, and there is also an observatory in France, so in Italy, which is called Virgo, and that's a European collaboration. Um, so this LIGO Virgo collaboration is what is received these signals up to now. But both these detectors are roughly in the northern hemisphere, and so therefore the signals that there is a when you get gravitational waves, you would like to localize the source where they came from, and if the detectors are both kind of nearby, then there is ambiguity. You cannot say where it comes from. The error bars are really huge. So ideally, a detector in the southern hemisphere would have been much better. And so in the beginning, the hope was that, well, maybe we can have a detector in Australia. And National Science Foundation in the United States was actually pushing for this idea with the Australian government to really have a third detector there, because then one would be able to pin much more narrowly uh, determine the location of the event from which gravitational waves were produced. So, but it turned out that that didn't work out, and I was in the know because the deputy director of the National Science Foundation was in touch with me about this project and about the meetings with the Australian authorities and so on and so forth. And then it turned out that when I got the news, just very soon after that, I came to India for a conference or meeting or something like, and I was at the Inter University um, Center for Astronomy and Astrophysics, Ayuka in Pune, and so I felt that, well, maybe India can make a pitch up there, and this was something that was also Indian scientists, particularly Bala Iyer and Tarundeep uh, sorry, Tarun Saurdeep, sorry. He um, they both were kind of very enthusiastic about this possibility, and so I tried to get more and more people interested. And I should say, lion's share of credit goes to the directors of Ayuka again, and the previous one, Naresh Dadish, but mostly Ajit Kembavi. At the time that this was happening, Ajit was the director, and so it turned out that Anil Kakorkar was the chair of um, their scientific board, scientific council, and so he was also happened to be there. And Anil Kakorkar is a high level, extremely high level scientific statesman in India, because he was the chairman of the Atomic Energy Commission and the historically important moments. And so I also had an occasion to talk with him, to discuss with him, and so on and so forth. So I had my role, and especially because I could talk with people in India, and I could also talk with people at NSF. And there was some panel that was in NSF, in which then I was asked to serve on that. And they asked me lots and lots of questions with other people from India also on the panel. But I was the one who was both in India and in the US. And so I had some role to play in that. There's no question about it. We pushed it. In those days, everything had to come through the 5-year plan. So we pushed it hard to get in I think it was 2012, wasn't like a 5-year plan. And it's a long story. And then finally, as you say, it has really been fully approved just a few months ago by the Indian government. Now, why is it important? Well, there are two different things here, I think. The first is just understanding the universe, science, etc., etc. And the second is the technology that associated with it, the development of science, of just technology up here. So it turns out that, let me start with the second one. It turns out that this project, LIGO India, LIGO, really needed to push the frontiers of technology, and that was one of the reasons why the United States put in $1 billion into it. It is not just pure science, but also push the frontiers of technology. There's laser technology. There is a materials technology. There are these threads from which these LIGO mirrors hang, and that will be extremely advanced technology. You have to do a thing called squeeze light, which is really, it's amazing that the things that one does with laser beams and quantum optics. The LIGO tunnel is 4 kilometers long, and you've got these laser beams they have to be extremely high intensity laser beams that have to go, but at the same time, they should not be so intense that they actually create a noise, because when the light hits the mirror shakes, and you want that shaking to be controllable. And there is just infinite number of incredible technology that is needed up here. And at the end of the day, one can actually measure the displacement of the mirror. How much displacement of a mirror can you measure? The relative displacement of the mirror that you can measure is the same as measuring the distance accurately to the width of a human hair. And distance between what? Distance between us and the nearest star, which is light years away. So it's really incredible technology that is needed in order to get these accuracies. And that pushes the frontier of technology forward. It pushes the computer science forward, because the LIGO data is huge and one has to invent, So because there's this frontier of technology, optics, materials, computer science, etc. So that is an important aspect. But to me, of course, an even more important aspect is just that we're learning about science, about our cosmos. So why are gravitational waves so important? Well, there are 4 fundamental forces of nature. There is gravitational field, there is electromagnetic field, these are known, and then there are fields forces which occur between atomic and subatomic particles, so-called weak force, which is responsible for radioactivity, and strong force, which holds the nuclei of atoms together up here. And it turns out that all these forces have associated messengers in the universe. So electromagnetic force has light associated, and light comes in various wavelengths. And that is where astronomy developed. We got regular light astronomy, we got infrared astronomy, we got ultraviolet, we got gamma ray astronomy, and so on and so forth. Then there is a weak force, and the particles which transmit this are called neutrinos. And there are observatories on the South Pole, which are called ice cube, because it is a huge, kilometers long tunnel in the ice in South Pole, where detectors are placed. And that ice cube observatory is looking at neutrinos. So we're understanding the phenomena, information carried by neutrinos. Astronomy, we're understanding the phenomena that through light that reaches us. And then with nuclear physics, it is really cosmic rays, and we're understanding phenomena that comes from cosmic rays. But gravitational waves open an entirely new window on the universe, which is not covered by these 3 messengers. So they will bring us signals that none of these messengers will bring us from. particularly, for example, black hole collisions. None of them actually tell us anything about black hole collisions. And we need gravitational waves to talk about black hole collisions. What happens in the very dense center of galaxies? Well, light comes from there, but light is scattered so many times before it reaches us that it loses memory. Gravitational waves don't. So we are learning completely new things about the universe, not only about exotic things like black holes, but also about centers of galaxies, galactic dynamics, also astronomical things like certain stellar populations and so on. So we're doing great work with gravitational waves, both in pure science and technology, and that is the reason why I feel that India can make it very good. It will be good both for India and it will be good for the world. Indian participation will profit the world as a whole in this international collaboration.
Sir, this question is this is not for scientific nahi hai, but I just want to ask, there are still a lot of people suggesting to young people that just go to other countries, start your research, go for higher study. If you want to do a better research and do better to get better opportunities, go in other countries. And this is a constant thing, that constant advice that we hear from elders. So does these kind of projects will help India to grow in a way that the Western countries or countries like US and European Union is doing, what these people are doing?
Right. So I think, in fact, Dr. Kakorkar is a very, is a science policy maker, leading science policy maker, and he emphasized that exactly is the point, that having a major, what they call a mega project on Indian soil makes a huge difference. Now, I think it is also equally important, and I hope Indian institutions will take up the challenge. And that Ayuka particularly had played a very great role. I hope all these institutions will continue to play the role of training young students and postdocs and creating the human infrastructure and so on. That is very important. But LIGO India opens up this window, this opportunity of doing things on the Indian soil. And I think that what you're saying is absolutely true, that it would, everybody else will come to India in order to use its facilities and so on and so forth. So you don't have to go to the LIGO sites in the United States to learn about how the detectors operate, etc., etc. It's the other way around. Students and other people will come to India to learn things about these things. So I think there's no question that these actually will enhance Indian science and its visibility and so on and so forth. Already just this last week's news about landing on the south pole of the moon has really elevated India's prestige and scientific proof of scientific capability to a very high level. And a successful LIGO India project, which really brings in new data with this level of sensitivity that was predicted, or even better, and that Indian scientists can actually take that data and make new predictions, new discoveries, will really push the scientific prestige to forefront and scientific recognition of Indian talent to forefront.
Okay, let me ask you something about two people. One is Roger Penrose and other is Stephen Hawking. So, how was your experience working with you? You told us about the Penrose, and I would like to know about how was the experience of working with Stephen Hawking and how people used to interact with him. And you also told us about you met him when he used to speak, not fluently, but he used to speak. You need to focus more on his words to understand what he was saying. So how was working with him, and a person who cannot move his body parts, but his brain was like he can solve problems and he can make theories.
Right. I mean, in fact, there is a very famous Canadian relativist by the name Werner Israel, who was also president of the International Society of General Relativity and Gravitation many years before me. He put it very nicely. He says that, well, this Hawking's calculation of Hawking effect was like Mozart composing an entire symphony in his head. So that is exactly the level of things that we're talking about. Really, something which is just absolutely at the forefront of human creativity and being done, in your head, I mean, as I was saying, because of the physical limitations. Yeah, so as you said, that I met Stephen. It turned out that, this review paper that I had written in as a graduate student with Bob Garosh, that review paper came at a good time because, I also mentioned to you that Stephen Hawking had just discovered this Hawking effect, and therefore he was getting more and more interested in quantum gravity. And so he actually read the review paper early on, and Martin Rees had written to me saying that he and I think George Ellis were reading the review paper very on. So, I mean, he knew about my work before I met him, and he was very interested in that, right, in quantum gravity. And that is why, when I visited Cambridge to give talks and such, which I did several times during those 2 years, I had he was gracious enough that I could spend some time with him. So, as you say, that even those days, I wanted to concentrate a little bit to understand what he was saying, but I think the discussions were always very meaningful, very, 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 very good for me. I had, in fact, I just turns out, in fact, I'm just finishing a paper, and in the acknowledgement, actually, I thank him because because actually the original ideas were something, not all the ideas, but one of the spark of the idea was something that came in a discussion with him. And it had to do with the asymptotic structure of space-time that you mentioned earlier on. So I think to me, it was always a very, very positive experience. Now, it was nowhere like the experience with Roger Penrose because I didn't live in Cambridge. I only visited there for a few days, several times, but still it was only a few days and not continuously. I also met him at conferences and things afterwards, and it was always very, very inspiring, as you say, to see somebody whose mind can use creativity is not, who has refused his physical limitations to affect his creativity, and it is really, so that I think is very, very, very inspiring. At one stage, you wanted to say something about Sudarshan also, or was it not you?
Just want to ask, there is someone whom I interviewed. It was the last interview of Rozender Talks season 1. It was Professor Pankaj S. Joshi. So when I talked about you to him, and he said you and him had a collaboration, and you people worked together for some time. So he also worked with Penrose and Roger Penrose and Stephen Hawking. So, how is the experience with? Is there a difference between working with American people and British people and Indian people? Is there a difference between all these three kind of people?
Well, to the first approximation, I don't think of people, scientists, as people that I'm working closely with as American or British or German or something. I think of them as scientists. So I don't think nationality is really matters, or at least in my mind. That is, I don't mean that there are the finer points in which people, of course, each nationality comes with some their own baggage and so. But these are secondary points. At the primary level, I think in terms of India, I sort of work much more with Badri Krishnan, for example, who is now in Germany. I worked with Madhavan Varadarajan, much more, who is now in Raman, has been in Raman Research Institute, Professor Raman Research Institute. And working with Madhavan is not any different from working with Ivan Aguirre, who is in the United States, is a very bright young faculty person. Not so young because about to become full professor, but still, I just don't see at the first approximation. I mean, of course, later the differences, but they're completely not so important. But what does matter is that in the field, I find working, discussing, and everything with people who are traditionally in general relativity or cosmology, even though now they're doing quantum gravity or quantum physics or working in gravitational waves or whatever it is qualitatively different from working with people in, for example, string theory. And I think it is not so much an issue about nationality. It's an issue about culture within subfields. And cultures within subfields can be very, very different. So, and these subfields transcend geographical boundaries. Again, there is a difference between string theories in the United States and string theories in Europe, but these are kind of in some less level. At the primary level, there is some certain similarity, which I don't find. And similarly, with general relativity and cosmology and gravitational waves people, internationally at a certain level, there is a very similar way of interactions.
Is there something which connects all the scientists so that they can get on the same page while they are with each other? And
it's science. I mean, that connects them together, right? I think, but this cultural thing that I said was that really is the following. It's a paradoxical thing, but it's a real thing. At the forefront of science, now this becomes as a little shock to people who are not scientists. At forefront of science, the forefront of science rather is driven by really prejudices, intellectual prejudices, not racial or color or something, but intellectual prejudice about what is fundamental. If there's a problem that is open, where is the solution like to lie? What should I look at? What is going to be the core, and what are the details? And different people might think different things are important, and what would be the most successful attack, if you like, line of attack. So, at forefront of science, these things vary, and once therefore given that can make a difference when scientists get together. Because if you are convinced, for example, that string theory is the answer to the world and everybody else is wasting their time, I mean, that is your right, because you are your own life and you should focus on something. But then discussions with your discussions with other string people would be fantastic. But your discussions with other people who don't share that point of view would be much more sparse. I mean, much more not interactive, and so on and so forth. So that is I'm just giving you string theory as an example. That can be anything else. If you're convinced that X is the center of the problem and everybody else is wasting their pop-up time, then anybody who is not in X, you are not going to interact so much. But if in fact there aren't very, very strong prejudices, then what brings together people is really the scientific issues, scientific open challenges and problems, and how to go about solving them. All right.
so, sir, there's a postulate that we read about the special theory of relativity, that the speed of light is a constant, and there's another thing that nothing can move faster than speed of light. So please correct me if I'm wrong.
No, so the statement is that speed of light is universally constant in special relativity. But that means that it does not depend on the relative motion. Like for example, if for example, you're in a train, as Einstein would say, and you throw a ball at another person in the train, then the speed of the ball in the train is going to be equal to something, say v, and if the train is moving with this particular platform at some speed, which say v prime, then the ball will be moving with the speed v plus v prime for a person on the platform. But the point is that if it shines light instead of throwing a ball, then the speed is exactly the same. Speed is c for both of you. When I said the speed of ball is v plus v prime, I was using Newtonian way of adding velocity. In special relativity, there's a correction, but the correction is such that if in fact the v prime was speed of light, then it is going to be the same for both of them. That's the statement.
So why I asked that?
But just a second. So the second question you asked was about nothing can move faster than light. No, special relativity does not say that. So what special relativity does say is that objects which are moving slower than light cannot be accelerated to speeds bigger than light, or even the speed of light. And similarly, objects which are moving faster than light cannot be slowed down to speeds less than light. That's what the particles say. That's what this postulate says.
So again, coming to the popular science, there is a term which is given by a scientist whom I'll name after completing my statement, that the tachyons. So in popular articles there is something that they don't they don't follow the rules of physics, and they try to break the rules of physics. These are the statements that has been used to define the tachyons. My question is that please tell us something about the tachyons and many things about the person who gave the tachyons.
Yeah,
about Dr. Sudarshan.
Sudarshan. Yeah, Professor Sudarshan gets called them tachyons. So the usual thing is just incorrect. The statement is that, special relativity, as I said, allows nothing. These particles moving faster than light. It's just that their physics is not their properties are not the same as the properties of the usual particles, which George Sudarshan also called tardions, because they're tardy. They're not moving as fast, so to say. So the popular science mixes the two things up. Instead of saying that their properties are different from the properties of tardions, they say that they don't obey laws of physics. That they obey laws of. Otherwise, how would you know what their laws are? Right? Because they are not laws of physics. They are laws of physics, and and people like Sudarshan have looked at them in some detail. But I think that this somehow in popular literature, tachyons is considered as being a great contribution of Sudarshan. And among the many great things he did, tachyon is probably among the lowest ones, right? His great contribution really has been, first of all, to quantum optics. Very early on, he talks about coherent states and various things which are absolutely first rate. And he often felt that he should have shared the Nobel Prize with Glauber on quantum optics. And then also with his discoveries, more importantly, his discoveries about the weak interactions, for which also a Nobel Prize was given, and I think it's appropriate, or for which you could have easily got a Nobel Prize, is what I should say. You should easily have won the Nobel Prize. So there are two major things that he did for which he could well have, he was deserving of a Nobel Prize, but for whatever reasons, there are many, many things that go into these prize decisions. So
have you what were your interactions with him, and what kind of person he was?
So I interacted with him quite a bit when I was in Austin. I was a student in Austin, and then years later, I was invited. I don't know, in 2000s or something. I was invited to give a colloquium again in Austin, and I gave a colloquium, and I saw him again and had an extended chat with him, and so on and so forth. And I've seen him in between. But I think Austin period was the one in which there was a sustained thing. I took a course with him. So he was my professor in a course on classical mechanics. It was, I also had lots of discussions with him. And the discussions with him were just not on science, because he was also very interested in the internal world in those days, at least what I call internal world in those days, and particularly in Vedanta. And he was in part responsible to get an Indian philosopher, very well-known philosopher named Raja Rao, to come as a visiting professor to Austin in the philosophy department. And Professor Raja Rao then taught a course on Vedanta, and that I went to, and sometimes Professor Sudarshan would also attend. I had lots of discussions with him about, and he was very interested in the spiritual aspects, and particularly not just Vedanta, but I mean, mainly Vedanta, but not only Vedanta. He was very interested in the transcendental meditation. And he was often a guest of Maharishi Mahesh Yogi in the Switzerland. And so he had these multiple dimensions, which, for example, Chandrasekhar was not interested in such things at all. So in particular, when I was a graduate student, he had, at that time, a spiritual master, and by name Padmanabham, but he was called Gurudev, and this was in Kerala. And when I was going to India, he urged me to go there, and so I went there. And in fact, I overlapped with Professor Sudarshan for a couple of days, or maybe more than that. I forget now. This was a long time ago when I was a student. At a little village. I think it was called Malakara, if my memory is right, but in Kerala. And we spent some time there. And I got interested in following about these Vedantic traditions, and I read a lot about Vedanta and so on. But for the longest time, it remained dry to me. I mean, I remember one instance, for example, when sitting in that room, there were several people, and particularly Professor Sudarshan, just sitting there in presence of this spiritual master, and Sudarshan had tears in his eyes flowing down, just being there. And nothing happened to me. I mean, and so I basically dropped out of that, because it was not for me. I mean, it may be perfectly fine for everybody else. But then I have always been interested in the internal world, and I followed that path quite a lot, and I follow it even now.
You had a 3-hour long podcast on the internal world.
You had one, okay.
Okay. So when there is a talk about the Vedanta, so there are a lot of people talk about that this was there in Vedas, and this was there in there. So have you ever encountered with the Vedas in a way, how like in a way that they can that does they explain anything about science? I just want to know about कि उनका actual में relevance है क्या? What is the teaching?
Yeah, so I think that I'm not an expert at all, but I should qualify that. But I think that in there's probably good literature on medicine, but I think as far as fundamental physics is concerned, it's too simplistic. I mean, it was a long time ago, so there's no criticism of the obvious. It is probably ahead of their contemporaries at the moment. But I think, I've seen this unfortunately even among engineering PhD or master students here, thinking that but it was in the Vedas. They had atomic weapons, and they fought the famous. When they talk about Astra and so on, they didn't, right? I mean, this guy, nuclear. It's a very complicated, sophisticated thing to understand. So if they had atomic weapons, they should have clear theory about atoms, and they should have understood quantum mechanics. They should have. I mean, how could I just don't understand why this is, but a lot of Indians just put two things separately. They can be doing science, and they can be talking about that everything goes in the Vedas. I think that is unfortunate oversimplification, and I think it does more damage than good, because then people who are serious about Indian thought dismiss everything. What is deep in Indian thought, in my view, this I can say from personal reading and everything else, like in Upanishads and so on, is the internal world, the states of consciousness. That is something on which I think India was way ahead of its time, is way ahead of psychology today, in my view. So that is, instead of focusing on the internal world where, you know, where there are true gigantic advances and true gigantic understanding, insights, for some reason people feel, oh, they had airplanes, they had atomic weapons. I mean, just stop it. And that makes absolutely no sense, you know. So I think that there are very valuable things, but they pertain more to the internal world than to the Patanjali cleansing of your consciousness. I mean, this is something that one should be proud of, and we should put that on forefront instead of this completely ridiculous claim. Because then once you put the ridiculous claims in front, then the world dismisses everything together. They dismiss Patanjali at the same time as this, and that is, I think, unfortunate. So I feel that we Indians could use more discrimination and claim credit where it is due and not claim credit where there is no credit.
Ji. Although I have a lot of questions to ask, and I have a very much long list of questions that I want to ask, but it's almost 2 hours that I have taken. So here I would like to wrap up with last 5 minutes of this podcast, and I would like to ask a few personal questions and few questions that are not related to science. I want to ask to Professor Ashtekar, and not to just Professor Ashtekar. I would like to ask this to a person that who has been a teacher, a student, and a researcher at all of that. And so these are some personal questions. What are your interests apart from science? If you were not a scientist, what you could be? Have you ever thought of it?
Yeah. So, I mean, what are my current interests? And there are two different questions you're asking. What are my interests apart from science? And secondly, if I was not a scientist, what I would be doing? That two different things. So I'm a scientist, and my current interest, I mean, I have written poetry. I don't publish it or anything of that sort, but I've done some readings here and there. I mean, and then, I just last year I did one. I'm on the board of directors of a new institution scientific institution that they have founded in south of France. And in the opening ceremony, there was a evening, and being France, there's always high culture. And so they asked me to read some poems, and which I did. And some older ladies actually came and said that they really enjoyed the poem, which I was very surprised by, because they're in English. I do speak French, but the poems, and I don't speak well enough to write poetry. So I've done that. I enjoy very much swimming, particularly in the mountain lakes. I like that, this tranquility, the cool, the high altitude, and so on and so forth. I enjoy that. But even in other waters, I enjoy that very much. I walk a lot, and usually when I walk, I often even close my eyes because it makes me more focused. So it's either of the two things. One is really continue to think about scientific problem that I've been thinking about, and so proving something or not, or finding an example or doing something. And very often, I don't mean 100%, but a large fraction of major new ideas have come to me while walking. And the other thing that I do while walking is really kind of a form of meditation, if you like, which is I'm now at a stage. I've done I've done some meditation over the years, and so now I'm at a stage in which I would like to go beyond what is called dharana, or uh, which is really concentration, and go on, perhaps try to go to dhyana, which would be true meditation, and that would be, so the very first part of that is really watching your thoughts. So that is something that I like to do while walking, for example, or while uh, I don't know, just sitting somewhere and relaxing that is my relaxation, if you like. So this is kind of a general thing. So my major interest, apart from science, and now I hope in the coming years more and more towards that, is really the states of consciousness and inner world. And I mean, I'll characterize as cleaning your own consciousness. And but then that's kind of the prerequisite. That's a part of shaucha. That is to say, it's really cleaning. I mean, just like you clean your body, you also clean your consciousness. But I think it is more about now about this dhyana. I would really like to pursue that very much. So this is all what I am currently, in the sense of I am a scientist, and then these are my interests. But if I had another career, what it would be? This is something that is a really strange question to ask, because it will be a different person altogether. And but interestingly, I would have liked to be a, a composer of music. When I grew up, I did not have any exposure to music at all, because in India, first of all, when I grew up, there was only radio, and on radio there was only film music, Binaka Mala or something, which I didn't particularly enjoy, so I didn't particularly listen very much. But as I grew older, after coming to this country and then also in Europe and so on, I got more and more interested in classical music, both Western and Indian. And I think that if I had not been a scientist, that would have given me the most happiness, being a composer of music. But that's a hypothetical life that we're talking about.
There's a lot of connection between scientists and the music. A lot of scientists loves to either listen to music, or either they want to play some kind of instrument, or sing. I just want to ask you, if this is possible, can you recite a poem of your for us?
Okay, I'll dig it out. Unfortunately, I may not be so easy, right, to find it. Um, yeah, I think it will be probably difficult to find it. Why don't you ask another question while I try to find it? Uh,
So, what are the places that you have been in India? So, for because
yeah, no,
you're
I can't find it. Sorry, unfortunately. Yeah, I
okay.
just searched in the computer, but it will take me a little while to find it. So yeah. So what are the question?
So, how did your food choices were influenced when you your father was a administrative officer? So you used to get he used to get transferred from one place to another. So, how your food choices were influenced by that?
No, that was not very much changed, because I think where he was transport, but he was in the civil service in Maharashtra. So we went from one region of Maharashtra to another region of Maharashtra, um, and basically, as I mean, in my day, certainly, I mean, the families had some food tradition, and one just ate that kind of food. And that was southern Maharashtra food is what I grew up. But since then, it has evolved incredibly a lot, because of being in many countries. I mean, both in I mean, in the United States, but also France. France influenced my food habits quite a lot, so I've changed a lot from since then. There are many, right? I mean, my students, I you typically, I mean, I've had, I think, between 70 and 80 postdocs, and more than 30 PhD students. And so together it's well over 100, and I've learned enormously from them, because when I work with students and postdocs, as you know, as is tradition in science that like with Bob Garosh and Roger Penrose and Chandra, we're equals. So we really work very much together. But I think in recent years, again, there are two different things. One is really when they were students, and then after they were students, right? I mean, or postdocs, something, because they become your colleagues, and for years they can influence you a lot. So, among people who have influenced my recent research are, Badri Krishnan, who is a professor now in in the Netherlands. He was in Germany. He moved to Netherlands recently. He works on gravitational waves, and Madhavan Varadarajan, who is in Raman Institute. So these are among the people that your audience will probably know. I can recite other names, but then there will be just some names which they don't have any connection with.
Okay, so not taking much time, I would like to end this session here. I don't want to end this session here, but due to some time constraints, I had to end this session over here. Thank you very much, sir, for sharing screen with us and for sharing a lot of information and anecdotes with different scientists. It was quite very fruitful and very informative for all of us who have been watching this podcast. So, thank you very much, and hope to see you again on the podcast with a lot of other stories, and I'll be sharing other questions, and we will be discussing a lot of other things. Thank you very much. Thank you, sir.
Okay, it's my pleasure, and good night to you. And bye now.